Hey guys, welcome to the next tutorial of trees concept. Okay, and in this tutorial we are going to see what is the B tree and its properties. And in next tutorial we are going to see an example for a B tree. Now, first of all, what is a B tree? It is a binary tree. Yes, it is a binary tree. It is a binary search tree. And initially we have first discovered what is a binary tree. And next step we have used the binary search tree where we can easily identify the required elements, right? And then in next process we have seen across AVL tree, what is an AVL tree and how to retrieve the elements even more faster. Okay, and this is the next level of concept, B tree. B tree is mainly discovered or invented in order to make the tree a even shorter one and to search very easily. Okay, if we are searching an element, we can search it very easily using a B tree. Okay, that's because the number of levels available in B tree is very less. Okay, yes, it is a binary search tree, and in this binary search tree we are reducing the number of levels so that the searching process becomes very easier. Okay, there are few properties in this binary search tree, and let's look after it. Okay, the first root property is the root node must have at least two child, which means that it must be a complete and full binary tree or binary search tree. It should not be an empty or partially binary search tree or complete tree. Okay, then next one, and at least two elements and at most m child node. M child means m is an order given to each tree. It may be an even number or it may be an odd number. Okay, so mostly, for example, if m is equal to 3, and which means that at least two child per node. Okay, so at least two child means we are having 3 child over here, so no usage. And then at most m child. So at most m child means each node can have maximum of 3 child. Okay, so this is child 1, this is child 2, and this is child 3. So this is a sample B tree where you can see that it is satisfying the B tree property as well as binary search tree property. So for example, let's take the binary search tree. So 1 and 2 are lesser than 3, which is correct. Okay, and 4 and 5 is greater than 3 and lesser than 6, which is at the middle of it. Okay, and 7 and 8 is obviously greater than 6. So all these numbers are satisfying the binary search tree property. Okay, now the first property is each node, the root node must have at least two child. Yes, it is having two child, a minimum of two child. Okay, and maximum of m child. So maximum of m child, 3 child are available as m is equal to 3. So this is also okay. Number of keys per node. So each node have a distinct value of number of keys. Okay, there is a maximum value and there is a minimum value. So what is the maximum value? Maximum value is m minus 1. If for example the root node is the m is equal to 3 means then we can have up to 2 child. Okay, so for example if m minus 1, so if the m is equal to 4 means then we can have up to m minus 1 3 child, sorry, 3 values per node. Okay, so here m is equal to 3, number of keys per node is equal to maximum of m minus 1. So m minus 1 is 2. So every node can have 2 values. Okay, if it is having 3 values, then we have to change the process. Okay, then I will tell you in the next tutorial by giving an example. Okay, and the minimum value is m by 2 minus 1. So each node must consist of any child. If it is having a child node, then it must have at least a minimum of m by 2 minus 1. If m is equal to 3, m by 2 is 1.5. 1.5 minus 1 is 0.5. We are rounding off the value to 1. Okay, so if we are rounding off the value means then every node must have, if it is having a child node, then it must have at least one value per that node. Okay, for example, if m is equal to 5, then m is equal to 5, then the maximum values available is m minus 1, which is equal to 4. Okay, then the minimum value available is m by 2, 5 by 2 minus 1, which is equal to 5 by 2 is 2.5, 2.5 minus 1, 1.5. So we are rounding off to 2. So each node must have a minimum of 2 values. There is no single value node available in those B tree where the m is equal to 5. Okay, now here in this B tree, okay, let's first go to the next property. So for next properties, all leaf node must be at the same level. Okay, so this is one property where it makes the B tree a lesser and shorter one, and here what we are doing is we are reducing the level of B trees. Okay, so all the leaf node must be available in a common common level. Okay, now so let's again wind up the refresh the properties. The root node must have at least 2 child node or at most m child node. Okay, so number of child having a C1, C2, C3, 3 childs are available, which is equal to the order m. Okay, next one, number of keys or number of values per node, maximum value m minus 1. So 3 is equal to m. So m minus 1 is 2. So maximum of 2 values available in all nodes. Okay, now minimum value m by 2 minus 1. Okay, and then last property, all leaf node must be at the same level, which is at the same exact level. All the leaf nodes where it doesn't have any child nodes. Okay. Now, for example, if we are going to add a new value in this B tree, for example, we are going to add the value 9. Okay. So 9 is obviously we are checking the root node, which is 9 is greater than 6. We are going to the right side of 6. So 7 and 8 is available. So we have placed the 9 over here. But this is not satisfying the B tree property. So in B tree property, we have a property called as number of keys per node. Maximum is m minus 1 only. So per node, only 2 values are available. So in this one, we are having 3 nodes, which is wrong. So what we have to do is, we have to move the middle one to the upper level. So we have to move the middle one to the upper level. So what we have to do is, m is equal to 3. So we are moving the 8 over here. Okay. So if we are bringing the middle value to the next level, then this becomes partitioned in 2 ways. Okay. So this becomes partitioned in 2 ways. So one becomes 7 and another value becomes 9. Okay. But you can see that the root node is having 3 nodes itself, 3 values itself, which is also wrong. So again, we have to remove the middle element and move to the upper level. Okay, so upper level, what happens is, so 6 moves to the upper level, the left hand side becomes 3 and right hand side becomes 8, and 8's left edge goes for 7 and right side goes for 9. So binary search tree property is also satisfied, and you can see that m by 2 minus 1. So minimum 1 value is available in all the leaf nodes. Okay, and all the child nodes. Okay, and all leaf nodes are available at the same level. Right. So this is the properties of B tree. Okay. So in next tutorial we can see an example of B tree. Okay. So until we meet in the next tutorial, it's Karthikeyan signing off.